Hello Chem students, this is going to be our second lecture of 4 for all these new methods that we're learning in chemistry that's making your life more complicated. We're going to look at corbonyl reactivity. There's some good things to learn out of that, and then we're also going to look at the end at another way of making an electrophile that's going to be important to us. And we're almost at the point where we can do just about anything we want for our course. What I want to look at on this slide is relative reactivity of carbonyl groups. And so by carbonyl groups, I'm generally talking about this C double bond O that you see in every one of these groups as you go down the line here. Okay, so that's a very important functionality in organic and biochemistry, and there's a lot of variety. It's probably half of the groups that you guys have to learn. You can see them just on this page: carboxylic acids, acid chlorides, anhydrides, thioesters, esters, amides. I don't have on here also aldehydes and ketones and even the nitriles. But here what I'm doing is I'm looking at the relative reactivity of what we call a carboxyl group. Okay, so this is a C double bond O, but in all these cases there's a heteroatom on the other side. Okay, this carbon here in many cases could be carbon or hydrogen, but on this side there's something that's different than carbon: oxygen, chlorine, oxygen, sulfur, oxygen, nitrogen. And so these have some similarity in that regard. Now the most reactive one is up here at the top, the acid chloride, and we've learned a way to make acid chlorides, so this is going to be real important. But how do you get to the top of the energy hill? Okay, well we're going to start with a carboxylic acid, which is a pretty stable group. The way we get up there is we use this very, very high energy compound, PCl3, phosphorus trichloride. There are other approaches to get up here, but our approach in this course is not to show every single possibility, but to present a possibility that gets us into this type of compound, and then we use that as an example for other things that you might want to come back to later. So anyway, we can get up here to the top of the hill. Well, of course, at the top of the energy hill, everything else will be downhill from that point. Way at the bottom, you see the amides are the most stable. So we want to understand this stability right here. Now, if you look at all these groups, each of these groups is potential leaving group that could leave, and the stability of those groups is sort of indicated by the acidity of their conjugate acid. So if I look at chloride here, that comes from HCl. That's a really strong acid, so that tells us that the chloride is very, very stable. Okay, and if I look at this leaving group right here from an anhydride, the carboxylate, that's a leaving group from a carboxylic acid. And even though the pK is positive, it's a fairly low number, so that tells you this is fairly stable. And our argument for that was it's resonance stabilized over the two oxygens. And then here's sulfur minus the conjugate acid is a thiol, pK of 8, that's pretty low. So that means the thiolate here is pretty stable. That's because the sulfur is such a big atom with a little bit of electronegativity in combination that makes it fairly stable. Oxygen from an alcohol, alkoxide here, is, it's not great, but it's not the worst either. So the alkoxide is moderately stable compared to other things. But you can see it's less stable than the thiolate here, and that's because it's a lot more concentrated charge. It's only using the N equals 2 shell. The sulfur is using the N equals 3 shell. The charge is more spread out. That was our original introduction to resonance, even though this isn't resonance. It's charge delocalization. And then if we get to the nitrogen, from an amine, it's a pretty big hill to climb, plus 37. So this is a pretty poor leaving group, but it's a possible leaving group. And this is important because in biochemistry, all of our proteins are connected by amide linkages that you see over here. So we want those to be strong because we don't want to dissolve when we walk out into the rain. But we want them to be weak enough so when we eat a piece of meat or something or some protein, our body can cleave this and use the amino acid building blocks to build our own structures. Okay, so here's just a reminder of how this carbonyl chemistry works. Here I have an acid chloride. Remember, that's the top of the energy hill. We get there from the carboxylic acid and phosphorus trichloride. And now what I'm going to do is I'm going to bring in those other nucleophiles to join up with this so that we can make the different functional groups that we're going to talk about, the anhydrides in this example. And as usual in my presentation, I give you one slide where I leave the details out, and then right underneath it I'm going to give you the answer. But this is the slide for you to think about what can happen. Okay, so if I look at these two, I'm actually giving you the step, but I'm not putting in the details. In a full mechanism problem, you would get this starting point, and you would get this final point, and then you would need to supply the intermediate stages plus the details. Okay, but if I have the details here, you can look and see what happens. So it looks like the C double bond O is joined up with this carbon that has the chlorine. And so that would tell you that we have to push electrons from this carbon over to this carbon, and then we're going to push up, and that would put a minus charge, formal charge here, and put a plus formal charge on the oxygen here. Overall, this would still be neutral, but it would have formal charge showing. Now, with a good leaving group and a minus charge oxygen, the oxygen can come back down. Oh, first off, let me show you there's resonance here, and that's why the carbonyl group chooses to react instead of this other oxygen, because we can spread out the charge. But if we have this O minus here and a great leaving group, we can push that back down, and it looks like that's what we did right here. And then the chloride is kicked off. Okay, so now we have a chloride minus. That could pick off this proton here and give the electrons back to the oxygen. That would give us our anhydride. Okay, so this is called acyl substitution, but hopefully you can fill in those details yourself. So I have those right down here. So I won't go through those all over again. I was just trying to talk the logic here, but you can see what it is. And so when you're learning this, what you need to do is come up here, try and fill in the details. You could do it on a separate piece of paper. And then you can come down here and look at the answer and check your work. If you're seeing mistakes, then you want to figure out, was it me that made a mistake, or was it you that made a mistake? Sometimes I make mistakes. So then you can come back up here, try it again, come back here and check your answer. Now I did this for most of the functional groups that I talked about on that first slide. So here I have a thiol, same acid chloride, okay? Remember, we can make a lot of acids now, and that means we can make a lot of acid chlorides. So you want to be able to generalize this. And the thiols, remember, we have our group here. We have 13 patterns, and 12 of them we can do an SN2 with the hydrogen sulfide here. And so that means we have a lot of thiols. So we can combine these together in a lot of different ways. Same idea, sulfur attacks the carbon, push up. Good leaving group, push back, kick off the chloride. This is very repetitive. Then I need some base in here to pick off that extra proton. So we'll use the thiol since it's probably more basic than the chloride. And then we get to the thioester, okay? Then there would be some formal charge here. So here's the answer. You would want to be able to push all these electrons. So again, try and do this problem. Come back and check your work. If you see mistakes, then do it again. Okay, until you get, and there's a lot of repetition, so you'll probably get better pretty quickly as you go through these. So here is an alcohol instead of a thiol, but it's not going to be much different. Okay, it's just an oxygen pushing instead of a sulfur. And so we would do the same thing, push in, we have formal charge, a minus and a plus. We push back, kick off the very good leaving group chloride, so it's very, very stable. And then we need something to pick off that proton, so I used another alcohol solvent to do that. Here's our ester. Now in esters, remember, we have other ways of making them. At our very first time of making esters, we used an O minus here. I only gave you one acid, acetic acid or ethanoic acid. We pulled off the proton and made the carboxylate, and then we attacked the carbon with the leaving group, the bromo leaving group. And so when bromide left, we were left with an ester. So we could cleave this bond over here on this side, but now we've learned that we could cleave this bond over here on this side if we have a leaving group at that carbon there. So now there's a couple of ways of making esters here. And so your repertoire is expanding, making life more possible, but also maybe more difficult. Okay, the steps are pretty much the same. Okay, acyl substitution again. Okay, over and over. This is a big type of reaction that we see in organic and biochemistry. Okay, we have another one to do. That's with the amines. So remember, on the amines, we have 13 different bromo hydrocarbons. On 12 of them, we can do an SN2 with azide, and then we can reduce the azide nitrogen to an amine and work it up to get another proton on there. We reduce it with lithium aluminum hydride, and then we work it up. That gives us primary amines. Later we'll be able to make secondary amines and tertiary amines. But for right now we have primary amines, and the nitrogen's even more nucleophilic than oxygen, so this should be even better. We go through the same steps. We have a minus and a plus. We push back, kick off the chloride. Nitrogen in the solution can pick off that proton, and we have an amide. Okay, So here's all the steps. You'll see this is very repetitive. I think if you just work through these examples right here, you'd have it down pretty well. Now on the amides, this is an especially important one. So I thought I'd talk just a little bit about the biochemistry of this. We have inside our bodies proteins that do all kinds of essential functions that need to be done for us to be living organisms. To build up our proteins, we have about 20 essential building blocks, amino acids. I think there's maybe 9 or 10 or so that we have to get from our diet, and our body can interconvert a lot of the other ones. So we have one amino acid connected to another amino acid connected to another amino acid, and this can go on from just a handful, maybe 8, 9, 10, to thousands and thousands of amino acids connect together in gigantic proteins. Okay, now it's kind of interesting. And the first one, we have 20 choices. Yeah, I'll actually show those on the next slide. Not that we're going to understand them or memorize them or anything. But if I pick a second one, then I have 20 ways of the first times 20 ways of the second. That means just connecting 2 amino acids together with our building blocks, we have over 400 possibilities. And each time we add another amino acid, it's 20 times that number. We would have 8,000 possibilities with 3 amino acids, 160,000 possibilities with 4 amino acids. And with just 10 amino acids, we have millions, billions, trillions, over 10 trillion possibilities. So you look at the power of nature. Nature has an infinite power to adapt and create new proteins and structures that might be better choices in terms of living organisms. Okay, and every one of these is an amide linkage that you see right here. Okay, that is an extremely important linkage. These are the amino acids. Okay, we're not going to worry about all of them, but what I'd like you to see is that here's a carboxylate at the end. This is the acid part, and here's an amine at the other end, and that's true of all these when they're by themselves. So in an amino acid, you actually have an acid built into the very same molecule as you have a base, and they kind of do what you would expect. The base picks off the proton from the acid, but when it does it, it makes it a minus charge on this end and a plus charge on this end. Now, if you have the amide linkage, you don't have that, because the amide nitrogen is not basic because of resonance with the oxygen. But you can see there's all kinds of little side chains. This one, glycine, is the simplest one. It doesn't have a side chain. But all the rest of them have different types of side chains that are important to the functionality of the amino acid in the body. If you look at these, are hydrophobic, 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 hydrophobic. Okay? Some of them have polarity, say like an oxygen, OH here. Here's an OH. Some of them have a thiol at the side, one of them right here. And here's a sulfide, or thioether. Okay, this is very important in, say, epigenetics of your DNA and stuff like that. This one's good at turnaround points on proteins. Makes like a bend, like sort of like a U-turn sometimes. We have some that have amide linkages at the end. We have aromatic rings, and then this aromatic from phenylalanine can be oxidized to tyrosine, which is very important. This oxygen right here can turn on a protein or turn it off when a phosphate is on. We have carboxylates at the end, a couple ways of doing that. And we have nitrogen at the end with a positive charge, a couple ways of doing that, well, maybe 3. So these are all real important, but that's something you'll learn more about in biochemistry. I thought I'd take one look. This isn't really our course, but it's kind of interesting. Ion channels are essential for our cells that are senses, that detect things. It's because a lot of times we polarize some process as part of the nerve impulse. But we have these ion channels that have a structure where on the outside, this right here is the cell membrane, okay, on either side, and then we have this protein embedded in it. So on the outside it's hydrophobic, some of those ones, and on the inside we have to get ions to go through. Sometimes it'll be potassium flooding out, sodium flooding in, or calcium and stuff like that. And so this has to be very polar to allow that, but there's gates and so forth that open and close and prevent that. Other parts of the protein might be very hydrophilic, and so they'll either stick inside the cell and mix with the water in the cytosol, or they'll stick outside the cell, mixing with, say, the blood. So you can see how complicated this is. They don't even show the individual amino acids. They just show it because it's ribbon after ribbon after ribbon after ribbon, and chains and so forth. There's so many of them, and it's so complicated. This is the molecule of a thioester, since that's one of our compounds that we're looking at. Now in biology, you might have seen this molecule before called acetyl-CoA. Very, very important molecule. But generally it's represented something like this. The S and then the CoA is so complicated we just abbreviate it with the CoA. This is what the CoA looks like right here. Okay, but this little 2-carbon unit is what is used, and the fact that it's on the sulfur allows it to be transferred on and off very easily. And so this can be used to build up your fatty acids. It can be used to make steroids. It's used in energy supply if it gets inside the mitochondria, and can make lots of ATP. Most of your ATP comes from metabolism of this in what they call the Krebs cycle or the TCA cycle. Okay, but this sulfur is a very good leaving group. Now in our course, the best leaving group is chloride, but sulfur is right up there close to it. Okay, so in biochemistry, we can't have acetyl chloride. This is acetyl chloride or ethanol chloride. Inside our body, this would fall apart to acetic acid and HCl, which would be not good for our body. So instead we have this guy. When you go down the line and look at this, there's a lot of functionality. Here's an amide, here's an amide alcohol. Kind of a funny branch. This is a very unusual quaternary branch. Phosphates, and then we got another ribose here, and then we got an adenine. So this thing's very complicated, but this is kind of the handle that the enzyme holds on to stick this just in the right spot to make the reaction work the way we need it to work. Okay? But anyway, that's future attractions of biochemistry. Now this is a slide you want to understand, at least in my course, and that is the relative reactivity of these carbonyls. And I've written them in order, so I put the acid chloride here, then the thiol, then the anhydride, then the aldehyde, then the ketone, then the ester, then the amide. Okay, that's our order right here. Now, the thing that these all share is a carbonyl group, C double bond O. So on every one of these, I can write a resonance form where I push the electrons to the oxygen. Now, if I did that, I would create formal charge. So this is not going to be as good as the original structure in terms of contributing, but it is a contributor. And I would leave behind a positive charge on the carbon with a minus on the oxygen. Okay? Now, in a lot of these, there's another heteroatom right next door that has a lone pair, and so that means we'll be able to write another resonance structure, a third resonance structure, and that moves the positive charge off of the carbon onto the heteroatom. So this should reduce the partial positive is what we're thinking, because it's spreading it out into another atom. And so I could do that every place down the line, except aldehydes and ketones. Okay, and if I come down here, the esters can do that, the amides can do that with the nitrogen. Okay, so there is no third resonance structure here, and that means just these two, and that's putting a lot of positive onto this carbon right here. So at first, let's look at these two right here. Excuse me, because we have a positive with nothing else. If I look at the difference between these two, there's a hydrogen here and a carbon here. Now remember what the carbon does when there's a positive charge. It inductively donates and helps stabilize this positive charge. So if we're thinking in terms of nucleophiles attacking this carbon, okay, this is looking like a more attractive target because it has a more partial positive because of that inductive effect. Now there's also a steric effect because when I look at it here, it's trigonoplanar with 120 degree bond angles. But if I am to bring a fourth group in, it's going to compress to a tetrahedral structure with 109 degree bond angles. So those are going to shrink. If these groups are big carbon groups compared to a hydrogen, they're going to be crowded closer to each other, and that should be raise the potential energy and slow the reaction down. So we have a steric effect and an inductive effect, both making the ketone less reactive than the aldehyde. And that's the way they present themselves in chemistry. Aldehydes are more reactive. Ketones are a little more stable. Now, if we go beyond that, say we go to the ester right here. So the ester, when we get here, actually has another structure where we borrow these electrons in from the oxygen, and that's going to remove some of the partial positive. Now, this is an ambiguous situation because the electronegativity of the oxygen pulls the electrons away. That should make it more partial positive. And the resonance effect pushes the electrons in. That should make it less partial positive. And so we have a battle here between inductive effects and resonance effects. So in our course, generally the resonance effects win. And what we have said from the start is that the resonance structure that has more bonds and full octets is better, okay, than this one. And so that means this should be less reactive than the ketone because the partial positive is less. Now the situation is almost identical for the amide in that the nitrogen can donate in too. So the difference is nitrogen donating versus oxygen donating. And hopefully it's pretty clear to you that the nitrogen is going to be a lot better at donating these electrons. The better it is, the smaller this positive charge is going to be, and the nitrogen will carry some of that positive charge. And in fact, in biochemistry, they generally teach that this structure right here is about a 40% contributor. Okay, that's almost half from the neutral structure up here. So this is a really powerful contributor. Also, it makes this carbon and nitrogen, sp2, trigonoplanar, and they're kind of flat in proteins. But so this is going to be a lot less reactive than an ester, and that's a resonance effect dominating over the inductive effect. So these four guys here, you should be pretty good at explaining these. And in fact, sometimes I actually put a hydrogen at the aldehyde because there's one aldehyde that has a hydrogen here. That's methanal or formaldehyde. And that would be the most reactive aldehyde of all because it has a hydrogen at both spots. So now let's come over and look at these guys because they seem to be out of place. I can write a third resonance structure in each case here. Now the problem for these guys is that chlorine is not in the same row as the carbon. Sulfur is not in the same row as the carbon, and they have different size orbitals. So I think that's on the next slide. Let's take a look at that one. Yeah. Okay, so here I have an acid chloride, okay? And I've wrote them out in 3D so that you can see the size of these orbitals a little better. So here's my first resonance structure, and then I move the electrons to the oxygen. So this is the resonance structure with a positive on the carbon. And then what we've been arguing is that the lone pair next to that can come in and share and make a pi bond here, and that moves the positive away from the carbon to this heteroatom that is here. Okay. Now the problem with chlorine and sulfur is they're in the n equals 3 shell. And so their p orbital is much larger than the carbon 2p orbital, and when I overlap, the overlap is pretty inefficient. Okay. Well, what that means is, remember, there's an inductive effect. Chlorine's pulling electrons away. And normally the resonance effect would beat that out. But in this case, the resonance effect is not that important. And so this carbon is more partial positive because it has the inductive effect of the chlorine pulling away with no benefit of resonance, or very little benefit of resonance. And so it's going to be real reactive in terms of nucleophiles attacking this carbon. Now if you come down here and look at this, sulfur is exactly in the same row as chlorine underneath oxygen. It's also a little bit electronegative. It's too big for this third resonance structure. So these guys are very much more reactive than what we see up here. Now this is pretty amazing to me in that this is the one that's nature picked. Nature picked its own little acid chloride, which is a thioester, whereas we use the chlorine. Okay, chlorine can only make one bond and you're done. But if I put a sulfur here, I can attach another group out here, and I have an infinite variety of things I can put here. And so nature has picked this one to be the acid chloride. Okay. If we look at the amide, okay, here I have the amide. Thus, the size of that nitrogen orbital is identical to the carbon orbital. And so when we overlap, we get very efficient donation. Nitrogen's not as electronegative as the oxygen, so it's better at doing this. You see the positives on the nitrogen. So this makes the amides less reactive. Now, the one that we haven't explained so far is the anhydride. So here's our anhydride starting point. Okay, it looks just like the ester. I have an oxygen next to the carbonyl. I said the overlap was very good because they have the same size orbitals, the n equals 2 shell. So if I bring these electrons in and push up, this looks exactly like the ester that we just did. But a big difference. The big difference is there's a carbonyl on the other side, and just as likely as the oxygen will spread out in that direction too. And so this oxygen is actually spreading itself over two different centers. So whatever its resonance effect is probably cut in half. Half to this side and half to this side. Remember, the resonance effect is competing against the inductive effect, where the inductive effect, just through the sigma bonds, the tug-of-war, pulls the electrons away from the carbon, makes it more partial positive. But I'm only getting half of the resonance effect. So in fact, this carbon is still pretty partial positive, even though it looks like it should be like the ester. Okay, so anhydrides are pretty reactive too. They're more reactive than the aldehydes. Okay. There's a very important anhydride in nature called ATP, and I'm certain that every single person has heard of ATP. It's what we call a mixed anhydride. There's inorganic, in terms of our thinking, inorganic elements here. So if you look here, I got the double bond O, oxygen, double bond O. Okay, that's what we call the anhydride linkage up here, double bond O, oxygen, double bond O. However, there's no carbon here. This is phosphorus. And I got it a couple of times, and I even have an ester on the end. And at the end of the phosphorus, we have these O minuses, O minus, O minus, O minus, O minus. These are going to repel each other. So to connect all these guys together, it takes a little work. Okay, your body spends a lot of energy trying to make this compound, adenosine triphosphate, because when it makes this compound, it has the ability to cleave these linkages and release that energy. It could do it at the first phosphorus, or the second phosphorus, or the third phosphorus. And the actuality is that it does it at all of those in different situations. Okay? And then down at the end here, we have a ribose, and then we have an adenine. And these are handles that the body can hold this in a certain spot and then allows some group and an enzyme to do its work, its business, at these different points right here. Okay? But again, that's sort of a biochemistry thing. I just want to point out that what we study in organic chemistry parallels a lot of what you're going to find in biochemistry. So at this point, we have a lot of bromohydrocarbons. I put X here because we can make the bromine into all kinds of things. We can make the bromine into an OH, an OR, an O ester. We can make it into a sulfur, SH. We can make it into a thioether, SR. We can make it into an amine. We can make it into a nitrile. We can make it into an alkyne. We can make it into deuterium. So there's a lot of possibilities here. And so we start with very simple hydrocarbons, but in chapter 10, we learn how to put free radicals on, to use free radical chemistry to put a bromine on. And so some of them, there's only one possibility, but when we got to the 3-carbon, we could put the bromine in the middle, and that would be easy because that was the more reactive spot. Or if we did a little bit extra, we made a double bond, we did anti-Markovnikov addition, we could put the bromine at the end, like this. And so for right now, this is our chemical tool chest to make things. You know, in reality, there's so many, there's infinite numbers of possibilities to do synthesis, but in our course, we're trying to limit it to just understand the reactions. So these are possibilities. We could put 2 bromines on, and if we put 2 bromines on, we can make 2 pi bonds with elimination. So this gives us a route into alkynes. Okay, and then we're also going to be able to use sodium cyanide from the start. Chapter 9, we've been able to do that. But in our very next lecture, we're going to start using carbon dioxide to make carboxylic acids. And so things are going to really open up there. So now we're starting to get into targets. And so this slide isn't to teach every single synthesis possibility, but instead it's to show how you can try and recognize the patterns that you see in these molecules down here with the patterns that you see up here in our starting possibilities. So if I look at this guy right here, first off I see 4 carbons. I see there's a different group here. Remember, this could be OH, OR, SH, SR, nitrogen. It could be a lot of things, but it's at that particular spot. So I come up here and I go down the line. I go, it looks like this one right here. And so what we're trying to do is recognize that this pattern somehow is feeding into this group right here. Okay, if I had a bromine here, I could bump it off with OH. If I have an ether, it actually has 2 problems because I got a pattern on this side. Sort of looks like this guy, but there's a double bond there. And then I have a pattern on this side. Certainly looks like a 3-carbon guy, like one of these, but then it has a double bond there. So those are things that you have to be able to manipulate and do. This one right here has multiple possibilities. I could picture this breaking it right here, say the phenyl ring plus 1 carbon. That would work for this, but there's more carbon out here. So I could come over here, maybe it's the 2-carbon guy, and I join something up here. That could be something like this. Okay, turns out that both of those are possible. After our next topic, we could do it either way. This guy looks pretty clear. I see a cyclohexane type of structure, so that would be this. Somehow I made a ketone here, but remember, if we could put an alcohol here, we can oxidize it up now, either with PCC or Jones. And then to the side here, this looks like enolate type chemistry. It looks like I added a 3-carbon group, say something like this right here. Okay, and so you could go through and do all of these that way. The sulfur, I have 3 carbons here, I have 3 carbons here. Looks like I have a ketone. Maybe I added on this enolate, this 4-carbon group right here, which looks sort of like that. This looks like the 2-carbon aromatic pattern with an X there. I have an ether, so we already did that, 2 sides. Here's a nitrile, so probably enolate chemistry, 3 carbons, and probably cyanide attacking this, and so forth. The amide, all we can do is acid chloride, so we would have to make this amine. The ester, we could make this alcohol and bring it up to the acid chloride, or we could take the O- carboxylate and bump off a bromine here. Alkynes, you can always clip at the end because this is stable minus charge at the end of the triple bond because of its sp hybridization, and then we'd have a leaving group here. You can do that on either end. So these are just little examples of that. This is pretty much the same thing. I put these little X's where you can make breaks. This is what your thinking has to start to look like. Okay, so I just went through those ones on the previous page. I won't do this all over again. But wherever you see those little lines, it's where you need to have some idea in mind how you could make that bond. Okay, which one would be the nucleophile adjacent to the carbonyl? Which one would be the electrophile with the leaving group, say a bromide? Okay, same patterns. Now, for some of these, we have to make minus charges, and we did this sort of back in the acid-base chapter. I just want to remind you, to make the carboxylate, we need a moderate base, so we use hydroxide. So this is a 100% reaction. We can make carboxylates. This now is a good nucleophile. To make an alkoxide, we need a stronger base. So here we use sodium hydride because this is not as acidic. So that's how we would make the alkoxide. To make the thiolate, it's pretty easy. We can start with a thiol. Now, can you make a thiol? We'd have to bump a bromide off with a SH. But once we do that, we can take this off with NaOH because this is moderately acidic. So that gives us a thiolate nucleophile. T-butoxide I just give to you. So this is big, bulky, and very basic. All it does in our course is to do E2 reactions at primary centers or secondary or tertiary. Okay, and that gives us alkenes. If I want to put 2 bromines on, I can take them off with 2 equivalents of the dialkyl amide. Unfortunately, when we do that, we have this acidic proton at the end, so the third equivalent, the dialkyl amide, pulls that off and gives us a minus charge. And that's why we need a workup step to come back in and put that back on. We have 3 alkynes that we can make, ethyne, propyne, and phenylacetylene, or phenylethyne. Okay, now for any of these, if we had them, we could use 1 equivalent and take off this proton. And now we have a good nucleophile that can react. And so, so far we've only reacted those with methyl and primary. At secondary, they're too basic and cause the E2 reaction. This is our dialkyl amide that we're making. Sometimes I have students make this, but not in our course. So in our course, you're just given, I just write this as 2 R groups. Okay, it's pretty famous. It's called LDA, lithium diisopropylamide. But in our course, we just call it dialkyl amides. And so we use this to either take off this proton here, or we use it to make enolates. Okay, and so we have ketone enolates, we have ester enolates, and we have nitrile enolates. And all of those make a nucleophilic carbon adjacent to the carbon heteroatom pi bond, because that stabilizes the minus charge. Okay, esters and ketones look pretty much the same. And then the nitrile, of course, the triple bond, can stabilize the minus charge too. Okay, we're going to learn a new one coming up almost right now. And that is we're going to make what we call sulfur ylids, and then a little later, if we have time, we'll make phosphorus ylids. We're going to use N-butyllithium, so this is a given. You can use this whenever you want. You can purchase this in all kinds of different ways, from just a small bottle to a whole tanker, a truck tankard full. But anyway, it's a super powerful base, the strongest base we see. And then what we're going to do is we're going to make these diphenyl alkyl sulfonium salts, and then we're going to pull off a proton on a carbon next to the sulfur. So here it's a salt because I have, whoops, that should be a bromide. I don't know what I was doing. I just probably dragged it down. This would be an anion bromide. And then we have the sulfonium salt. So we pull that off, and now we have the minus and plus balancing each other. We call that a sulfur ylid. So let's take a look at that. We're going to use these sulfur ylids to make epoxides, and that's going to be our third and last category of electrophiles. Okay, and then we'll use all these things in synthesis. So this is the way it's going to work. Okay, you're given diphenyl sulfide, and generally these sulfides are really stinky compounds. Okay, unfortunately, I've worked with various sulfur compounds, and they're pretty smelly. They get into your hair, your clothes. They just smell bad. But anyway, very good nucleophile. The body actually does something like this too, although in a slightly different way. But this will attack this carbon. Now, how many of these guys do we have? We have 13. Only 12 of them will work because this is an SN2 reaction. The T-butyl bromide doesn't work, but the rest of them do. So that means we'll be able to attach 12 different groups to this sulfur. And this gives us the sulfonium salt that I was talking about, where I have the right bromide instead of lithium. Okay, so you can make this, put it in a bottle, and some of them you can even buy from a commercial company, some of the simple ones. But for us, we have these 12 patterns that we can make. Now, once we make it, we get ready to use it to make the epoxide. Okay, we use the N-butyl lithium. Oops, forgot a 2 here. It should be CH2. And then that's going to attack and pull this off. So 100% reaction. Look at this. Compare the Kas of each of them. 10 to the 15th, we're on this side. So here's our sulfur ylid. Okay, notice the nucleophilic carbon sitting right here. All right. Now what we're going to do is we're going to present it with aldehydes and ketones. Remember, we make those from alcohols and PCC, pyridinium chloral chromate. So we have 12 different possibilities we could make here, and we have 12 different possibilities we can make here. And so we're going to combine these in a lot of different ways. So nucleophile, just as we've seen, attacks the carbon. Remember, that's why we have different relative reactivities based on the partial positive of this carbon. So we attack, we push up. Now, what's going to happen is this O- can slam back down on the adjacent carbon where the sulfur is, because the sulfur is such a good leaving group. So it leaves as the diphenyl sulfide that we started off with. Okay, and in the process of doing that, it makes a highly strained ring. Okay, so we're quenching the minus charge. We have a good leaving group, and so that compensates for the high strain that we put into this ring. So this is actually an ether. Okay, if you look at it, carbon, oxygen, carbon, but it's a really special ether. We call it an epoxide. Has a lot of ring strain. Okay, which makes it very reactive, and then we can use it in other reactions. Here's the steps right here. Now notice what I did here. I have 2 different carbons that have joined together in the middle here. All right, that joining was right here, and in this side right here with the carbonyl, I have 2 carbons, and on the side with the sulfur, I have 1 carbon. Okay, when I get over to the end, I can't tell that. I just tell there's 3 carbons here, but I can't tell which was the donor and which was the acceptor. And that means I can actually switch this around. So I could do this in a different way. I could put the 2 carbons on this side with the sulfur and the 1 carbon on the side with the C double bond O. And if I attack in here, I can close back down on that carbon, kick off the diphenyl sulfide, and I get exactly the same compound. So these guys, there's more than one way to do some of these reactions. It's just a matter of how did you choose to do it. It's not a right or wrong way to do it. Or it could be because it's a commercial product. Here I did 1 carbon on the sulfur and 1 carbon in the carbonyl. So this just shows you another pattern that we can get to. Okay, this would be the most simple epoxide possible. Sometimes they call this ethylene. If I had CH2 double bond CH2, that would be a common name of ethylene. So they call this ethylene oxide. And this is an epoxide. This also goes by oxirane. That's another name for these epoxides. We won't worry about naming these. Okay. So here I did it with 3 carbons on the carbonyl, just trying to show you some different patterns. This is the variety of this reaction. Okay. They all come from the diphenyl sulfide attacking some carbon with a leaving group, the bromine. And so we have 12 different ways of doing this. Then we can attack over here, and we end up with 2 carbons on this carbon on one side, and then an open CH2 on the other side. Okay, so this will be important in terms of how they react in the target molecules that we're looking at. You're going to have to pick out these features to be able to decide which one you have to construct. I showed some of them, not all of them, but I showed a lot of the possible sulfur salts that we can make. Now if you look at this, here's the 2 phenyl groups, okay, and here is the carbon group that we joined up. Okay, here's the carbon group that we joined up. I just condensed the two phenyl groups down so that it would be easier to look at this. Here's the carbon group. So this is the 2-carbon one. This is the 3-carbon in the middle. This is the 3-carbon on the end. This is the cyclohexyl one. This is the phenyl with 1 carbon to the side, the benzyl pattern right here. And then we have the 2 carbons right here, so we could do it at the first one or the second one. And then we have the allyl pattern, and then the allylic guy here. And I don't have the 4 carbons with 3 carbons in a row, 1 carbon branch. I didn't put those in here. But those are also possible. Okay, so we can combine all of these. These are potential nucleophiles. Not yet. They're salts. I would have to take off this hydrogen that's not shown within butyllithium. Then I would have all these as minus charges, carbons, and then I could attack all of these carbonyls. So I could bring them in, push up, and then close up to make the epoxide with 1 carbon, 2 carbons, 3 carbons in the middle, 3 carbons at the end, and so forth down the line. A lot of possibilities here. Okay, so this is a burden on beginning students. Now, remember, we start at the salt. Actually, we start at the sulfur, diphenyl sulfide, and attack the carbon with the bromide. And that gives us a salt. Then we pull that off, and so then we have this nucleophile. Now, I picked just the 1-carbon guy to join up with all these guys so that you could see the different possible patterns. And I wrote that out as a CH2, like I have here. Okay, so CH2, 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 CH2. In all these cases, I'm using the same sulfur ylid. But in fact, remember, we can switch this around. I could do it the other way. But this just shows you the variety of epoxides we can make now. So when you look at this, say when you look at an epoxide like this, you have to be able to split right here in the middle and make one of these carbons a nucleophile, and that will be the sulfur ylid. And make the other carbon a carbonyl. You can see where it would connect right here. And then you could turn it around. I could make this the sulfur ylid, and I could make this the carbonyl right here. Okay, but I would get to the same compound using those two strategies. All right. Now, this is an ether, as I mentioned. I just want to point out 2 very common important ethers. One is diethyl ether. A lot of times people just call this ether. They don't say the diethyl, or they say ethyl ether. So this is very common, boils very low, about 35 degrees, just about 10 degrees above room temperature. In fact, this used to be used as an anesthetic to put people under, say, for a surgery or something. In 1955, I actually got my tonsils taken out with ether. They knocked me out with the ether by dripping it on a little gauze with a wire mesh over my nose and mouth. So I can actually remember that. This is a similar looking compound, except they've tied these 2 ends together, okay, back here. That changes its properties quite a bit, okay, because permanently I have the dipoles pointing towards the oxygen here. Here I have these methyl groups swinging around. That's going to bump it away from other nearby ethyl ether molecules. Okay, so that's going to change their properties. But these are 2 very important solvents. But if we come down here and take a look, okay, here's THF, tetrahydrofuran. Notice the boiling point 66, and then look at the boiling point of diethyl ether, about 35. If you look at the polarity, a lot more polar with the THF, the tetrahydrofuran, because it's permanently in this shape right here, and the dipoles are always pointing in this direction. Okay, here things are distorting as these methyl groups rotate around, a little bit smaller dipole moment. Now, if we went over and compared oxirane, or ethylene oxide, to the dimethyl ether, same situation, permanently pulling these back, and so that makes the boiling point relatively high. It's a simple small molecule. But if I take that away and just allow these methyl groups to be more spread out, then the boiling point drops almost over 30 degrees. That's quite a bit. And the dipole moment is much larger here too. Okay, so this is going to be a little more polar molecule, and we'll be attacking one of these carbons in SN2 reactions. So at this point, we're almost at the point where we have everything we need for our course to build up molecules. We've learned about all these electrophiles. Remember, electron loving. These things want to be attacked by electrons. So if I have a bromine there, the carbon can be attacked, the bromide's pushed off, very stable leaving group. And that can be SN1, SN2, E1, E2, all these different ways that we've learned. We have methyl patterns, a methyl pattern, primary, secondary, tertiary, allylic, benzylic, and so forth. Our second one that we've just gone through and learned about is the corbonyl patterns. So we have aldehydes, and we have ketones, and we have esters, we have acid chlorides, and we have thioesters, and we have nitriles. So we have this whole other class, okay? And we tend to attack the carbon and push the electrons to the oxygen, the heteroatom. Down here we would attack and push the electrons to the nitrogen. And now we have our third pattern right here, where we can attack these carbons that are attached to the oxygen, because the oxygen is a leaving group, although not generally a great leaving group as an O-, but we have 27 kcal per mole of ring strain in here. So if we attack, that's a big bonus to get. We pop that open and boom, we're down 27 kcal. Now, since a lot of these are SN2 reactions that we study, we're always going to be attacking the less hindered side. So here it makes no difference, but here this would be the less hindered side. Here this would be the less hindered side. And so we'll be attacking that side. Now, in combination with all these electron acceptors, we have all these electron donors. And I'm only emphasizing the carbon and hydrogen ones here. I'm not looking at sulfur and nitrogen and so forth. So for carbon, we've learned cyanide. We got that one for free right at the start. We have to make the acetylide. We have to pull that proton off. Enolates, we got to pull off the adjacent proton. So we had ketone enolates, we had ester enolates, we had nitrile enolates. This is the one we're going to study next. This is really going to revolutionize our possibilities. Okay, so this is going to be a big deal. There's a couple of spots where this doesn't work so well, and so we'll bring in cuprates to show those, take care of those. And then we have all these hydrogen donors. More commonly used is lithium aluminum hydride and sodium boryl hydride. But I don't tend to use those in our course because I want to see where you make the reaction happen. So I propose using the lithium aluminum deuteride and the sodium, that should be a sodium boryl deuteride. Okay, so this is nucleophilic hydride and these are nucleophilic carbon. Okay, so that brings us to the end of our second lecture. We'll start in next time looking at magnesium and copper and some organic synthesis stuff. Okay, so thanks for listening.